Hi, this is Dr. Montgomery with a lecture video on kinetics for Chem 202 at BBC. This is one of the major concepts covered in Gen Chem 2, Chem 202, and so it's really important that you have a deep understanding of what kinetics is before you're done with the class. The main thing that it focuses on is something called the reaction rate, which is the change in the concentration of, let's just say, stuff in the reaction mixture with time. So it can be a decrease in the concentration of a reactant or an increase in the concentration of a product. For example, if we look at a reaction that's the decomposition of N2O2, so N2O5. Okay, so that would be this blue trace here. Okay, so if we have this reaction, it's just starting, N2O5 as the reactant on the left side of the arrow, and then NO2 and O2 as the products on the right-hand side of the arrow. Very simple reaction, a decomposition reaction. The blue trace is following the concentration of the N2O5 as a function of time. So at initial time 0, the concentration of the N2O5 is 0.02 molar, and you can see it's decreasing as time increases, as the reaction is allowed to go forward. Simultaneously, the concentration of the nitrogen dioxide and oxygen is increasing, but the rates of everything are not the same, right? The N2O5 is decreasing at a much slower rate than the NO2 is increasing, and the O2 is increasing at a much slower rate than the NO2 as well. So the rate of the chemical reaction basically tells us how fast everything happens. We can look at specific parts of, let me rephrase that. So not specific parts. So we can look at the rate in terms of each participant in the reaction. So we can consider the rate of formation of the oxygen, which is going to be the delta concentration of oxygen over time, right? So the delta symbol means change. So this is a change in the concentration. The brackets, remember, brackets are meant to represent concentration. So the change in the concentration of the oxygen would be the concentration at the end of some allowed time period minus the concentration at the beginning of that time period, with the delta T being the time period over which that change occurred. So it's always final minus initial. So that would be the rate of formation of the oxygen. The rate of formation of the NO2 is going to be, again, final minus initial over delta T for the concentration of the NO2. The rate of decomposition of N2O5 is going to be a negative value because its concentration is decreasing in time. Its final value over that time period is going to be less than its initial value, and therefore the difference is going to be negative. So we put a negative sign by convention in front of the reactants to indicate, basically to take care of the negative sign that would result from subtracting the two concentrations. And then also conceptually, we understand that if a rate of an expression, this is called a rate expression, has a negative sign in front of it, that's representing the rate of change for a reactant and not a product. So you can see that here, the time interval, let's take a look at the NO2, right? So if we look at this time interval from 300 to 400 seconds, T final would be 400, T initial would be 300, so our delta T would be 100. Our final concentration is pretty close to 0.02 molar. Our initial concentration is, somewhere between 0.015 and 0.02 molar. And so the T final minus T initial would be roughly 0.02 minus 0.016, let's say. And then that would calculate out to, we would just divide those two numbers, and that would be 0.0037. Now, if you've taken calculus, you know that this is an estimate, right? Because this line is curved across that time period. This is an estimate, and the smaller the time interval, the more accurate that estimate is going to be. So we kind of think of it as an instantaneous reaction rate. You see that the rate is changing as a function of time, right? The curves are curved. The rate is higher at between 0 and 100 seconds than it is out here between 700 and 800 seconds, right? We have much less vertical change out here than we do down here for all of the participants in the chemical reaction. So what tends to happen is that the rate decreases with time. Usually, well, I don't mean to say usually, the rate of the reaction is faster at the beginning and slower at the end. So you can say that the rate depends on concentration, and it's going to decrease with decreasing concentration. So a reaction rate depends on a number of different things. Depends on what product or reactant you choose to measure the rate. It depends on the concentration of that product or reactant. So if you measure the rate when the concentration is high, then the rate's going to be greater than if you measure it when that concentration is low. It depends on the time, right? So if you measure it early, it's different than if you measure it later. And so those are the main things that affect the reaction rate. And so what we try to do is write a more general reaction rate that takes into account, okay, scrap that. We're going to get there. My thought was a little bit ahead of myself. What we need to talk about right now is a general rate that takes into account like on this slide, for example, trying to represent the overall rate of the reaction and reflect the fact that the concentration of the nitrogen dioxide is changing faster than the other things. So that's called a relative rate expression. And it looks something like this. If we have this reaction, C6H12O6, which is basically a fermentation, is that what that is? Yeah, fermentation of glucose. So the fermentation of glucose will generate ethanol and carbon dioxide. We see that the stoichiometry is 1 to 2 to 2, right? So for every 1 molecule of glucose fermented, 2 molecules of ethanol will be formed. Or we can say that the formation of ethanol is twice the rate of consumption of the glucose. So when we say that, we can think of it this way. The formation of the rate of change of the ethanol is equal to twice the rate of change of the glucose. And because it's consumption of the glucose, we have the negative sign. Now, writing these relative rate expressions gets a little bit confusing because you have to do that. You have to put the coefficient out in front. And for me, I like to just kind of say the sentence and then write it out as I'm saying it. But your textbook shows a trick, which I think is pretty useful. So bear with me one second while I navigate to it. Is this it? Yeah. So students find it a lot easier to remember to write it this way. So if your coefficient in front of reactant A is this small a, then you're just going to put that in the denominator of the relative rate expression. So this A goes here, and because it's a reactant, that's the one that gets the negative sign. So you get negative 1 over A times the delta of A, which this book isn't using the brackets for concentration, but I use those brackets. There they are. I guess maybe because it's not talking about a real molecule, it doesn't have the brackets in there. But so the change in concentration of A over the change in time. So in other words, the coefficient just becomes a denominator in the rate expression. I think students find that a lot easier to understand. So let's take a look at it at this example. This is in your iodine clock lab, but I don't think that it's the same reaction. It may be, but the virtual lab that you're using this term may or may not be the same reaction as this. If you happen to be watching this video at a later time, when we are not doing online education because of COVID, this is more likely to be the reaction that you're going to be doing in your experiment. But either way, this is a great example. We decide to measure the rate of reaction of this particular reaction, and we decide to measure it in terms of the bromate ion, the BrO3 ion. And so let's think about how to write the expression in terms of the BrO3 ion. So if you think about it, you can say for every 3 molecules of iodine formed, 6 ions of iodide are consumed. So iodine, for every 3 of iodine, 6 of iodide are consumed. So we can say the rate of iodide consumption is twice the rate of iodine formation, right? So we can just, it's 6 to 3 or 2 to 1. So the rate of iodine consumption is, right, the equal sign represents the is in the sentence. The rate of iodide consumption is twice the rate of iodine production, or we could also write this, we could write 1 over 6 delta I minus over delta T is equal to 1 over 3 delta I2 over delta T. And then obviously that would change. You'd have 1/2 over here, which is the same as having the 2 here. Let me show you real quick what I'm talking about. So we could write, as I was saying, we could write 1 over, we have a negative sign out front if we're talking about the iodide. So we'd have negative 1 over 6 delta, the change in the iodide concentration, delta T, is equal to 1 over 3 delta iodine over delta T, right? And then 1 over 6, 1 over 3, we can simplify. This would be 1 over 2. So negative 1 over 2 delta T would be equal to right? And then we can, since the 2 is on the denominator over here, we can just bring it to the numerator on the other side. We'd have negative change in iodide concentration with time is equal to twice the change in the iodine concentration with time. So that's what I mean. Those two expressions are the same. So if you want to, when you're looking at the expression, looking at the chemical reaction, balanced chemical reaction, you can just take the coefficient and turn it into a subscript in the rate expression. I'm going to skip this slide because we're not doing this lab this term. Okay, so we're moving on to this slide, which is the dependence of the equation on the concentration of each reaction is called the rate law. So let me explain this a little bit more. The rate law includes all of the reactants. So what we looked at before is a relative rate expression, and now we're talking about a rate law. Those are two different things. They're trying to get at similar information, but the rate law is the same no matter what. So with the relative rate expression, it depends on which reactant and which product you decide to measure or look at. Whereas the rate law is sort of, it's a single, unchanging expression to describe the rate of the reaction overall. And so here you can see it's written like so. We say the rate is equal to, and then we have this little bit here, which is one of the possible relative rate expressions. And we say then that is equal to this part here. This K obviously is a constant, and hopefully you're used to K being a constant by now. A is the first reactant, B is the second reactant, and if we had more, we would go on C, D, E. It would all be included in the in the rate law. Raised to some power, A is to the M power, B is to the N power. So each reactant in the rate law is raised to an unknown power, and it's up to us to determine the values in this expression. So we're going to learn some techniques for determining and writing rate laws. Okay, so right now I'm just sort of introducing a new thing. It's not intuitive. It's a way that scientists decided to represent the rate of a chemical reaction. And you want to think of K as a proportionality constant that helps to sort of make units work properly. And also that's a number that is determined experimentally. Some of your questions will be asking you to determine that from data, and you may be determining that in your virtual lab. The exponents M and N indicate how sensitive the rate is to changes in the respective concentrations of A and B. So for example, the smaller the value of M, this exponent here, the smaller the value of M, the less sensitive the reaction is to a concentration change for A. So we change A a little bit, and m is small, so the rate doesn't change very much. But if m is big, like say it's a 3 or a 4, then when we change a little bit, we're going to be cubing, or what do you call it when you take it to the 4th power, that concentration change in terms of the rate change. So the bigger that exponent is, the more impact that particular participant in the chemical reaction is going to have on the rate. Those are called the order, or orders of the reaction with respect to a specific reactant. So if m is 0, right, anything raised to the 0 power is just 1. So a to the 0 would just be 1, and that would mean that the reaction doesn't depend on that reactant. So if m is 0, the reaction doesn't depend on a. If m is 1, the reaction would be linear with respect to a. So there would be a constant rate of change. When we change a by a certain amount, the rate would change in a linear relationship. If m is 2, right, when we change a, the rate would square. So that would be a quadratic relationship in terms of the shape of the function. Similarly with b, right? If n is 0, then the reaction doesn't depend on b. If n is 1, then the reaction is linear with respect to b. If n is 2, etc., etc. So again, that's called the order with respect to the reactant. The sum of your exponents is the overall reaction order. And so the overall order gives us an idea of how sensitive the reaction is to concentration changes overall, whereas the order with respect to an individual participant in the reaction or an individual reactant, obviously just gives us an idea of how sensitive it is to that one reactant. Some reactions are really sensitive to concentration changes and others are not so much. These exponents are determined experimentally, and you can't figure them out looking at stoichiometry. Let's just take a look at some practice problems and think about how the order of these reactants is changing. So let's write, no, we're not actually writing them yet. Okay, so in this we're being given the rate law. And in this rate law, we're told that the reaction, this is how you would say it, the reaction is second order in nitrogen monoxide and first order in O2 or in oxygen, nitrogen monoxide, oxygen. So hopefully you guys remember how to name things from Chem 201 because I like to use the names. But you get that it's NO and O2. So it's second order in NO, first order in O2 in this reaction here. Now, it's just a coincidence that the coefficient on the NO is a 2 here. And the exponent is a 2. That's not necessarily going to be the case. Look at the second one. We have a coefficient of 2 on the NO and a coefficient of 2 on the H2. The reaction is second order with respect to NO, but only first order with respect to the H2. So the coefficient, again, does not stipulate the order. In this one, it's linear in both reactants. So first order with ICl, first order with H2. Here we have a first order N2O5 dependence. Now, what is our overall order? We're going to sum together the exponents on these in the whole rate law. So here, the overall order would be 2 plus 1 or 3. Again, this is 3. This one is going to be second order. Here we would have first order. This one would be second order. So you see you add them together. Now look, this is really interesting because we have a 1/2, right? And something raised to the 1/2 power means it's the square root of that. So it's going with the square root of the concentration of bromine. The sum of 1/2 and 1 would be 3/2. So the overall order would be, we would say 3/2 for the hydrogen-bromine reaction. So the way that we actually find these orders is by testing a reaction at different times. So you can see here the evolution of color in a given chemical reaction. And so presumably these are reactions that were started at different times. So this reaction was started first, and it's been going longer. And so the color has gotten most intense in this one on the left. Whereas this one over here on the right was started latest and has not been running as long, and therefore its color is least intense. So we have a sort of decreasing intensity from left to right, right? If you think about it, going from right to left is sort of like a snapshot of each step along the reaction. This is what it would look like at the beginning. These are more like the middle, and this is closer to the end, right? So some reactions are nice because you can observe the evolution of the reaction based on the color change. Not all reactions have color changes, but for those that do, it's really fun to measure that color change. So we have techniques that allow us to do that. Something called UV vis, ultraviolet and visible absorption spectroscopy. I'm trying to remember if we did a virtual lab with that in Chem 201. But if you have a hands-on lab with BBC, we do some absorption experiments where you put samples into a spectrometer and you measure how much light they're absorbing. So this sample would not be absorbing very much light, and this one would be absorbing a lot of light. They're absorbing in a color that's sort of opposite the one that they're showing. So I guess this would be in, let's see, red, blue, green. So opposite it would be like a blue-green color is where this solution would be absorbing. Anyway, you can measure the amount of light absorbed in a reaction using one of those instruments. And so you get data from those kinds of experiments where you know the concentration of participants in the reaction at different time periods. Here's an example of some data that we can use to determine the orders of the reaction with respect to the different reactants. So what you do is you start the reaction. In this set of data where we've started the reaction 4 times, we've run it 4 times, and we change the concentration of one thing in the reaction each time. Our initial reaction starts with 0.015 molar NO and 0.015 molar O2. The second one doubles the concentration of the NO. The third one, it holds the O2 concentration constant. The third one doubles the concentration of the O2 and holds the NO concentration constant with respect to the first trial, right? So we're kind of referencing this first trial for the remaining. And then the last trial doubles both. And then what we do is we measure the rate of the reaction. So how does the concentration change with time, right? So we measure the concentration initially before the reaction starts. We allow the reaction to run for a certain amount of time, and we measure it again. We take the difference in concentration and divide it by the amount of time. Pretty straightforward experiment to run. So we get our initial run 1. Our first run has an initial rate of 0.048 molar per second. Okay, so that means the concentration is changing 0.048 moles per liter per second. In the second run, the rate changed from 0.048 to 0.192. So it increased. So the increase in the concentration of the nitrogen monoxide caused the rate to increase. Now the question is, in what way does this change, right? So when we double the concentration of the NO, we observe. We want to be able to see if there's a correlation, or if we can make a correlation. That's not the right word, but for example, if I divide 192 by 48, I believe I get 4. So when the concentration doubles, the rate quadruples. That goes as 2 squared, right? So 2 squared would be 4. So this is second order. And I'll show you how to figure that out. I'll go over that again. This is a little bit difficult, I think, for students to catch on to that by me just saying it out loud, or you trying to do it in your head. Okay, so what we see is a doubling in the concentration, the initial concentration of the NO causes a quadrupling in the rate. Let's take a look at what happens when we double the O2 concentration. So for this, we want to make sure that we're holding the NO concentration constant. So we're going to compare runs 1 and 3 here. When we looked at the dependence on NO, we compared runs 1 and 2, which was okay because the O2 concentration stayed the same. So in runs 1 to 3, our NO concentration is staying the same and our O2 concentration is doubling. What happens to our rate? It doubles, right? 0.048 times 2 is 96. So this concentration doubled, which doubled the rate, which is a linear relationship. The same thing's happening to the rate as is happening to the concentration. So that would mean it's first order in with respect to the concentration of the O2. Okay, so that means that the overall order would be to the third, and so when we double both, we should get a much, yeah, we should be able to figure that out, but I'm not sure exactly how to say it, so I'm not going to. I don't want to mess it up. But you see that the rate increases even more when we double both of them. Okay, so that's all of this, I think. Second, and that is second order in NO, which is what I said already. First order in O2. So if you've determined the exponents, right, then you can calculate K. So what you do is you substitute in the values for the exponents. Let me do that for you on the here. So what we know is that our rate, always when you write these rate laws, you're going to write rate, and then you're going to write equals, and you're always going to have this constant of proportionality K. You're going to also have all of the reactants written in the rate law, and so we have, I believe, what do we have? We have NO and O2. So it's going to depend on the concentration of the NO, and we're going to have the exponent up here that we determine, and the concentration of the O2, the product of those two, and the exponents are the orders. So we said it's second order in NO and first order in O2. So essentially M is equal to 2 and N is equal to 1. Now what we can do in order to find K is we're going to substitute in some data. So let's do just from trial 1. And in trial 1, we saw that our rate was 0.048 molar per second. So we're going to substitute that value in, this number right here. So rate is substituting in 0.048 molar per second. And we don't know K. Then we're going to substitute in the concentration of the NO, which was 0.15. And I don't need the brackets anymore, right? So we're multiplying that by 0.015 squared. And then we're going to multiply that by the concentration of the O2, which is also 0.15. But in this case, the exponent is 1, so obviously I don't have to write it. Okay, so then we just can solve for K. So K then is going to be equal to 0.048 molar per second. And this unit is molar here, and this unit is molar here. So we'll have divide 0.015 molar squared and 0.015 molar. So you can put that into your calculator. Once you pause the video, put it in your calculator and make sure that you're getting the same answer as me. So we have try to make my calculator smaller so it fits on the, there we go. 0.048. We're going to divide 0.015 squared, and we're going to divide again by 0.015. So let's just check that I put it in right. Divide 0.048 by 0.015 squared, and by 0.015 again. I could have just done 0.015 cubed, but this is the way I did it. Either way works. So this is pretty large. We have 14,222. And what are the units on K here? So 14,222, we should probably round that to 2 significant figures. So let's just put zeros in for these two. It's 14,000. And so we have seconds in the denominator. We're going to get 1 molar canceling, and then we're going to have molar squared in the denominator as well. So the way to write this that makes it look nice is to use reciprocal, so s to the -1 to the -2. And so maybe you've already clued into the fact that the units on your constants are going to be different depending on the order of each reactant in the overall, in the rate law. So for example, if we only had a 1 as an exponent on this concentration, then we would only have a single m in the denominator. This would be m to the minus 1. So our rate constant is 14,000 per second per molar squared. All right, so here is another set of rate data. And see if I can move it out of the way. It looks like I somehow, there we go. Here's another set of rate data, and I'm challenging you to use these to determine the rate law. So this is an example problem, and you guys can ask me to do that for you in class after you've given an attempt. I'm going to end this video here for now and post it, and then I'll pick up with the rest of the content in the next video. Bye for now.